And here we are back in topics and statics. This time we're going to talk about the reduction of a distributed load. So far, all the forces we've talked about, we've assumed that they're concentrated loads, which means they act at a single point on an object. Now we're going to consider a more realistic load where it's distributed over some area. All these types of forces are caused by just real forces applied this way. We'll analyze the most common case of a distributed load, which is a uniform load along one axis of a flat rectangular body. So we're taking out a lot of the complications, but essentially what this does is I get a loading which is a function of x and has units of force per unit length. So in this figure, this function here is the loading, it's the pressure as a function of x. And it all adds up to be some equivalent force Fr. And we have to figure out where to place that force and what the magnitude of that force is. So considering an element of length dx, in other words, I'm just looking at this little piece right here, a little rectangle. It has a width dx. The magnitude of that force dF is this function, the loading function, W of x times dx. That's the area of that little blue rectangle. The net force on the beam is found by adding up all those different rectangles as I go from 0 to L. And so that's just the integral of W of x dx from 0 to L. That's the area under the loading curve. So the force dF will produce a moment about point O, which is x times dF. So the total moment is given by the integral of x dF, which is x W of x dx. Assuming that the force acts at the point x bar, it will produce the moment about O given by this. Right? Essentially what I'm saying is that, okay, I've got this distributed load. It's a little hard to draw. We've got some distributed load over here acting on this beam. And what I claim is that that's equivalent to a single force, Fr, acting on the beam at a point x bar. So this is W of x. So I claim these two things are equivalent. In order for them to be equivalent, not only does that force have to be equal to the integral of that W of x, but the moment also has to be the same. And so the way I find x bar is by setting those two moments equal to each other, setting this equal to this, and then solve for x bar. And when I do that, that's what I get. The coordinates called the centroid or geometric center of the area. And we'll talk more about centroids later in the course. Right, that results in the distributed load being reduced to a single force located at a specific point, which is what we were trying to do, simplify it. Now, because we haven't talked about centroids yet, we're not going to do a whole lot of stuff with all these integrals. Instead, we're going to look at rectangular and triangular loading diagrams. And so what you need to know about a rectangular loading diagram is that the centroid is right in the center. It's in the middle. So here on the left, I've got a rectangular loading just 10 feet wide. So on the right, I replace it with that force located at 5 feet. For a triangle, a right triangle, which is what we've got here, it has a width of 6 meters. The position that I'm going to have to put this thing at is going to be 1/3 of that distance from the fat end. So here's the fat end of my triangle, the tall end of the triangle. I'm going to be 1/3 of the distance from there. So 4 meters from the left, 2 meters from the right. So let's work a problem. It'll make more sense. So here's a loading applied to a beam. Find the equivalent force and its location from point A. So I'm going to measure everything from point A. So I'm going to use a coordinate system that looks like this. Here's my x. This is 0. So I'm going to break this up into 2 pieces. One's going to be this triangular loading, and one's going to be this rectangular loading. So the first step is to find what is the equivalent force. And the equivalent force is the area inside that picture. So we'll call this W1 and this one W2. So the equivalent force for 1 is going to be the area of that triangle. That triangle is, area of a triangle is 1/2 the base, which is 6 feet, times the height, and the height is 150 pounds per foot. So it looks like 450 to me. 450 pounds. F2 is the area of that rectangle. Well, the area of a rectangle is the width, which in this case is 8 feet, times the height, which is 150 pounds per foot, which is how much? 1,200. Now, where do I place those 2 forces? Well, the x bar 1, the distance is 6 feet. From the left, it's going to be, that's the smaller end, so it's going to be 2/3 of that distance, which would be 4 feet. X bar 2, it's going to be right in the middle of that 8 feet, right, which is 4 feet from that end, which is 10 feet from A. So in other words, I can replace that distributed loading with a beam and 2 forces acting on it. Where this is x1 bar, this is x2 bar, this is F1, this is F2. So I claim that that's equivalent, but now I want to replace that with a single force. So I find the resultant force, Fr, which is just F1 plus F2. And technically this is all vector stuff, but they all point down. So what's that going to be? That's going to be 1,650 pounds. Where does that need to be located? It needs to produce the same moment about A that those did. So x bar times that resultant force needs to be equal to x1 bar times F1 plus x2 bar times F2. So x bar is And if we plug all those numbers in, we get, what do we get? We get 8.36 feet. And that's the basic plan. Next time we'll start talking about equilibrium of a rigid body.